Hi students, in this note set we're going to talk about mutation, and you can find our relevant reading in Bio Chapter 10, Section 16. First, let's start with a definition. A mutation refers to any change in the nucleotide sequence of a cell's DNA. If you recall, the DNA molecule is hundreds of millions of nucleotide base pairs long. And if you can picture in one of those pieces of DNA called the chromosome, where you have hundreds of millions of nucleotides, if any one of those is changed from its original sequence, you have a mutation. During the course of a normal human's lifetime, we experience thousands of mutations. So it's not all that rare of an event. It's just that our DNA repair enzymes very often will pick up and fix the mutation that has occurred. So mutations, they can occur naturally from errors when a cell copies its own DNA to make new cells, and we'll study that in the next unit, how DNA copies itself. Mutations don't necessarily mean that you've been exposed to high energy radiation. It just happens naturally. But there's also external sources of mutation, such as high energy radiation like X-rays or ultraviolet rays, excessive exposure to which can damage or even delete nucleotides from your DNA. So if you spend a lot of time near the Chernobyl disaster site, you're more likely to experience mutation than you are if you lived far away from that disaster site. Or, this is a common one, if you're at the beach and you do not put on sunscreen, not only will you sunburn, but you're subjecting the DNA of your skin cells to higher levels of high energy radiation than you would otherwise. Think back to our study of evolution. This was some time ago. But mutations in DNA are the primary drivers of new genes. If you didn't have mutation, we wouldn't have new genes, some of which are beneficial and some of which are deleterious or not beneficial. Generally speaking, if you're copying DNA, mutation or mistakes in copying are rare and random, but they're the only way that new genes are produced. Picture this, students. Let's say during the course of an entire school year, in a certain class, let's say a science class, I asked you over 1,000 questions. Over 1,000. Let's say that you're a DNA replication enzyme and you make just one mistake out of over 1,000 questions asked. In class, you would be getting an A++. But in terms of the frequency of mutation, you'd be doing very badly. It's only about 1 in every 10,000 DNA nucleotides that are copied that a mistake is made on average. Of those rare and random mutations that do happen, most of them make no difference in the sequence of amino acids that make up proteins. Remember, in our mRNA codon table, there's a lot of duplication. There's 64 triplets of mRNA bases that code for just 20 amino acids. That means there's more than 3 times as many triplets as there are amino acids. And if there isn't a difference in amino acids, that means there's no difference in the protein sequence. Well, even of those few mutations that cause a change in amino acid sequence, even of those that don't produce any effect, more likely than not, it would cause a harmful mutation, which means that that gene, that is the DNA sequence that provided that protein or amino acid sequence, and therefore that protein, would die off with the individual. But of the very, very, very slim number of DNA mutations that produce a beneficial effect, well, then that gene, which produces a beneficial protein, would be more likely than not to get passed on to its offspring. And that's how we get evolution happening. Many mRNA codons code for the same amino acid. And so many mutations don't make any difference in the final sequence of amino acids. Take a look at leucine. Leucine has 6 codons that code for it. UUA, UUG, CU, anything would all code for leucine. So if you changed the last nucleotide in any of the CU somethings, it wouldn't change a darn thing. That type of mutation, where there's no change in amino acid sequence, is called a silent mutation. So, for example, if a mutation causes an mRNA codon to change from CCU to CCA, let's find those. CCU, CCU codes for proline. If that were to change to CCA, you still get proline. You'd still get the same amino acid in your protein. Point mutations. These are mutations that substitute just one nucleotide for another. Only that one nucleotide is affected. But there are other kinds. Frame shift. A frame shift mutation shifts the way the DNA sequence is transcribed. You can insert a brand new nucleotide where there wasn't a nucleotide previously, and that results in an entire frame shift mutation where you're adding nucleotides. Deletion. If you totally delete a nucleotide that was present at one point and is not present thereafter, all of the remaining downstream nucleotides are shifted, meaning the amino acid sequence would very likely be affected. Let's give some examples. Let's say your original nucleotide sequence in DNA is T, A, C, T, G, C, A, G, G, T. And let's say the new nucleotide sequence is T, A, just like above, C. So thus far, the first 4 nucleotides are exactly the same. And then, for some reason, the nucleotide replication enzymes put a cytosine in the place of a thymine, but then everything else is the same going downstream, G, C, A, G, G, T. Well, if that type of mutation happens, it's only at that one point where you've got a T in the original DNA sequence and a C in the mutated sequence that there's a change. Now consider this one. Let's say, again, the same original DNA sequence, TAA, CTG, CAGGT, and now the new sequence is TAAC, so same first 4, but then all of a sudden we've added a new nucleotide. We just inserted an extra C, but then thereafter it reads the same, TGCAGGT. That means every amino acid that's produced from the messenger RNAs downstream from that insertion are going to be shifted. Their frame doesn't read the same, so we call it a frame shift. Lastly, let's take a look at a deletion example. So the original DNA sequence, once again, is TAAC, so that much is the same. But now, take a look at this. The original sequence went TGCAGGT. The new sequence cuts out the T. Alrighty. The T got crossed out. Here it is down here. It got crossed out. And so it still reads thereafter GCAGGT, but you've shifted every single codon thereafter from what it was at one point. That will affect greatly, much more greatly than simply a point mutation, all of the downstream amino acids. The homework assignment that I'm going to ask you to look at will have you consider different kinds of mutations.